This work is about new Steganographic attack for additive manufacturing design files, and additive manufacturing is popularly known as 3D printing. My name is Marcin Polski, and this work was conducted in collaboration with my colleagues Lynn Graves, Jacob Gatlin, Anthony Zhao, and Moti Young. American Society of Testing and Materials, or short ASTM, defines additive manufacturing as a process to join materials to make objects from 3D models or digital designs, usually layers upon layers. AM is popularly known as 3D printing, and probably have seen one in your lab or lab of your colleagues. What is less known fact is that AM is very popular also in manufacturing, and it enjoys annual growth rate of 26% for past 29 years, and it is currently accepted for manufacturing of parts from ranging from pure models to parts for safety critical systems like jet engines. And you can manufacture with EM parts with a variety of materials ranging from polymers through composites to metals. AM security is a fairly new field of research that was pioneered around 2013-2014. And so far, 3 security threat categories have been discussed in the research literature. This is theft of technical data, sometimes referred to as intellectual property theft. It is sabotage and illegal part manufacturing. And all 3 have been discussed in the research literature from attacker perspective, defense measures, and also legal implications of each of them. In this work, we expand the threat landscape with a completely new category, data infiltration or exfiltration. And specifically, we are showing that it is possible to embed arbitrary data in digital design files used in additive manufacturing without changes to geometry described in these files. Before I go into specific technical details of our work, I would like to spend a few moments explaining why is this a realistic threat. If we are thinking about desktop 3D printers, something that you can buy for your home, it is fairly inexpensive. You can buy one for as little as $200, and for decent quality it will cost you up to $5,000. At the same time, if we are talking about industrial grade, professional, high quality 3D printers, the price ranges are much higher. For polymers or composite 3D printers, you have to pay something in the range between $10,000, it is entry price, up to over $200,000. With 3D printers that operate on metals, nothing goes under $500,000, and it can go as high as $3 million per piece of equipment. At the same time, all 3D printers are fairly universal. You basically only need digital design files, and you can manufacture arbitrary design without reconfiguring your equipment. This is very well suited for low quantity manufacturing, and therefore a variety of outsourcing models have evolved. In commercial sector, we see AM is provided as a service, or it is used as a service to manufacture commercial parts. At the same time, we also see increase used in home 3D printing, where people like you and I can download files for free from sharing websites, or buy license for manufacturing specific design and 3D print something at home. So we see huge increase of exchange of digital design files in additive manufacturing or 3D printing. It should be no surprise in additive there are different digital design file formats that can be used. However, from all the variety, both in home as well as in industrial settings, the most prevalent and commonly used file format is STL. This is a legacy file format that describes a three-dimensional object as a set of triangular facets. Each facet is defined by its 3 vertices, each of which is defined by its 3 coordinates in a 3-dimensional space, or x, y, and z. In addition to these 3 vertices, we also see a vector, normal vector, that defines which surface of this facet is facing outwards of the object. and together with the sequence in which vertices are listed, this normal vector should follow the right-hand rule. On the right side, you see an example of a STL file in its ASCII representation. Here you see only an excerpt with just two facets shown. First, we started analyzing STL file format by trying to identify what sources of entropy that we could use to embed arbitrary information in STL files. Specifically, we looked for sources of entropy that will not change or affect 3D geometry at all. We also wanted to find sources of entropy that can be applicable to both ASCII and binary STL file formats and can be used for also blind recovery of embedded messages. We identified several sources of entropy like facet order, vertex order, normal direction, and number representation. And according to our constraints, we selected vertex order as the most representative and most satisfying to all our constraints. So let's start by looking at how raw steganographic channels can be defined using the source of entropy. On the right side, we see an example of a triangle facet. Obviously, it should be completely agnostic to the order in which vertices are listed. However, because the order should also correlate with the normal vector of the facet according to the right-hand rule, it restricts only to 3 different sequences in which vertices are listed, or cyclical rotation of its original representation in the STL file. This allows us to encode in each facet up to 3 distinct values. However, for encoding these 3 values, we need to convert our data to base 3. If we want to avoid this conversion, we could also encode just 2 values in this single facet, but in this case it will also have a cryptographic drawback of not even distribution. And on the right side, on the button, you see this 2 binary value encoding or 2 values encoding per facet, where you have 2 different representations for bit value 0 and 1 representation for bit value 1. One more thing needs to be mentioned on this slide. For blind decoding, we need to introduce order so that we can distinguish between different sequences in which these vertices can be listed. In our work, we assume a well-formed STL file. In this particular case, it means that all vertices that define a facet are residing in distinct locations in 3-dimensional space. This assumption allows us to define order, or like in this case, define max function for 2 vertices that for giving x, y, and z coordinates for each vertex can decide which of them we consider as a maximum compared to another one. At the same time, this definition of order also allows us to distinguish between 2 cases. In one case, when the first listed vertex is the maximum from all 3 vertices, we can declare that it is bit value 1, and otherwise we can say that it is bit value 0. And this corresponds to our example or representation in the STL file on the previous slide. I should also note that there are different ways how this order and also bit assignment can be defined. This definition allows us to define a pseudocode shown on the slide, how a single bit value can be encoded or decoded from a single facet. On the left side, you see encoding function. First, we check which bit value should be encoded. If it is 1, we then check whether first vertex listed represent maximum according to our definition. Should it be the case, nothing else needs to be done and we return. Otherwise, we identify which of the other 2 facets is the maximum value and we rotate accordingly. If bit value 0 should be encoded, we again check whether first vertex is maximum 1. Should it be the case, we need to rotate, otherwise we already have bit value 0 encoded and we just return. Decoding function is somewhat similar, much simpler. We first check whether first vertex is a maximum one. If it is the case, this represents bit value 1 encoded, otherwise bit value 0. To transition from a single bit to single byte value operations, we need to make several considerations. First, we need to decide in which order we operate on bits of individual bytes. Obvious choice is most significant to least significant or vice versa, but also arbitrary sequences are possible. Second set of consideration is that we need to advance inside of STL file, so that we need to keep track of our current position or our current facets that we are working on and update accordingly on which facet we are operating, either writing value or reading value from. On this slide, you see a pseudocode of how byte operations can be implemented. On the left side, encode byte function takes a single parameter, byte value. We first initialize our bit mask with a single most significant bit set, and then we iterate through 8 bits. Inside of the loop, we first get access to the next facet in which this particular bit should be written, and we check by comparing our bit mask with the byte value whether this particular bit should be set to 1 or to 0. And according to this, we call our encode bit function with either 1 or 0. Afterwards, at the end of the loop, we shift bit mask by on position to the right. Decoding is somewhat similar. We first initialize our return value to 0, and we initialize our bit mask with MSB set, and we iterate through 8 bits. We first get next facet from which bit should be read, and we check whether return value is 1. If it is the case, then we set corresponding bit in our return value, and afterwards at the end of the loop we shift our bit mask to the right, and upon completion of the loop we return our byte value. At this point, we have almost all tools that we need to encode arbitrary length byte stream into STL file. However, before we do this, we need to consider following two facts. First, STL files are of different length, and therefore this means that they are of different encoding capacity. And second, also the data streams that we want to encode in STL files can be of different length. So we have two questions to resolve. First, will it fit in the STL file as the data that we want to embed? And second, how can we know how long is the data? And here on this diagram, you see a very simple solution. First, we store the size of the encoded byte stream, and then we concatenate or follow with the byte stream that should be encoded. So this message is then encoded in a STL file and can be transmitted, and correspondingly on the opposite side, on the receiver side, it can be decoded accordingly, first retrieving the size of the byte stream and then decode the corresponding amount of bytes from the STL file. Here you see a pseudocode of how this approach can be implemented. We assume that secret is stored in a binary file. Therefore, our encoding function takes 3 parameters. First, file name of STL file that will be carrier. Second, file name of this binary file with the secret. And the third one, what is the destination file that will contain both description of STL plus embedded information. First, in the function, we are reading our secret file and determine what is the size in bytes. Then we are doing similar with the STL file. We are loading this in internal data structure and determine what is the encoding capacity. And because we are using facets to encode a single bit per facet, we divide the facet count by 8 to determine what is our encoding capacity in bytes. Afterwards, we check whether encoding capacity is sufficient to embed the entire message plus the size field. Should it be the case, then we are navigating to the beginning of the file, of carrier STL file, encode our secret, encode all bytes by byte, and then we can save our internal structure in a destination file. Decoding is somewhat similar. We load our STL file. We determine, we first stick to the beginning of this file and read first 4 bytes to determine the size of the secret, and afterwards we decode this number of bytes in an internal array, which can be afterwards saved in an external file. Everything I have taught up until now defines a raw steganographic channel on STL files. But let's take a look how it can be used in different categories of attacks and which properties these attacks can have. We can distinguish between 3 categories of attacks. In what we call weak attack, we assume that secret is embedded in STL file plain text. But even in this scenario, we can make a claim that if investigation only triggered in the case that manufactured part is distorted, then defense will fail and encoded information will pass through checks. In regular attacks, we consider scenario when embedded information is encrypted and placed in this way in a STL file. Also here, we assume that if crypto system that was used for encryption was strong, and even if investigation is trying to determine what information was embedded, but crypto key was not found, for example, it was not present in the malware, then defender cannot determine what information was embedded in a STL file. And the third and the most strongest category of attack is strong attack. Here we assume fully encrypted steganographic channel. Here we assume key and data encapsulation mechanism, and we can make a claim that even if malware is fully analyzed to the extent that public key of the recipient is found, also in this case, defender cannot determine what information or size of the information that was embedded in the STL file. So let's take a look at how strong attack can be implemented. Part of it is fairly classical. We derive a temporary message key from random number and a public portion of a shared secret. Then we use a session key to encrypt our entire data using a state-of-the-art encryption algorithm like AES-256 in CBC mode. We also derive a number that later can be used in conjunction with the private portion of a shared secret to recover the session key. Part of it is somewhat different and applied to our scenario. The data that we are encapsulating consists of several parts. Like in previous example, we have portions that describe the size of the secret that is embedded, and we also need the pads as this data with pad 1 and pad 2. So altogether, size, secret, and 2 pads are comprising multiple of block size. The difference between 2 pads is that pad 1 is multiple of the blocks that is completely encrypted and embedded in the other payload in STL file, and only portion of pad 2 block is embedded in STL file because the capacity of STL is not necessarily multiple of the encryption block size. On the receiver side, we also see a combination of classical and applied approaches. Classical portion is that first we recover our KIM portion of the embedded information and use it to derive a message key, and then this message key is used to decrypt the rest of the information. However, the rest of the information, like I mentioned before, is not necessarily multiple of the block size. Therefore, we only take the portion that is multiple of the block size and we decrypt all this portion, with exception of the pad 2 with 2 stars. And from this decrypted portion of the message, first field is our size field that determines how many bytes in the remainder of decrypted information is actually our transmitted secret. Everything else are pads, and they can be discarded. As I mentioned at the beginning of this talk, a critical requirement for this work was that embedding of information in STL file shouldn't disrupt manufacturing process 3D printing or 3D printed part itself in any fashion. And we evaluated this experimentally. We embedded Python programs that implement the proposed approach. And for the evaluation, we selected fairly innocent-looking carrier STL files. This is Stanford Lucy. And as a payload, we selected controversial design files for Liberator, Plastic Gun. We took several files, archived them, and encrypted this archive with a password. And then we embedded this file in carrier STL file. Afterwards, we also extracted archive from the carrier STL file, and we compared the MD5 checksum of both archives, and they were identical. So this was proof that we can both embed and recover information from the carrier STL file without information losses. To validate that the proposed approach doesn't interfere with the 3D printing process and also doesn't affect the manufactured part at all, we actually 3D printed this design. So we used two different slices and two different 3D printers. On the left side, you see a side-to-side comparison of graphical output in Cura slicer, other slicer by Catalyst X. And on the right side, you see also physical output of 3D printing using Stratasys Dimension Elite 3D printer. And you see here front and back of the Lucy using original design file and also design file with embedded archive with Liberator gun. Other 3D printer was Wolfsbot Stack 6. And in both cases, we couldn't distinguish between digital output and physical output of a product using original design file and design file with embedded information. I slowly come to the conclusion. The proposed approach has several real-world implications. With the increased proliferation of AM outsourcing, also at-home manufacturing, sending or downloading STL design files become something common and very innocently looking. Therefore, it can be also used to exfiltrate stolen information from highly secure environment, for example, by sending innocently looking STL file to a shell company, or downloading from the internet malware or tools into a secure environment. At the same time, in order to thwart law enforcement agencies to collect some evidence, some information can be stored in STL files as well. And obviously, it has implications to the AM security field as a whole. For example, it can be used as a communication channel for technical data theft. As you can imagine, this is only first from what we plan to be a series of works in this research direction. One of the considered works or follow-up works is to explore superposition of discovered covert channels. In some scenarios where restrictions are not as tight as considered in this paper, these different covert channels can be used to increase both encoding capacity and also robustness of the encoded information. Also, we think that the same covert channel can be used to actually protect information, for example, by embedding watermarks and fingerprints that will assert digital right ownership. Also, especially in conjunction with this malicious use, we need to develop two tools. One is to sanitize information regardless of whether some information is present or not. We need to be able to remove any possible information, and at the same time this tool should ensure that it doesn't interfere with the printability and printed object. We also want to develop a distinguisher that will, for a given STL file, actually decide whether it is probable or not that additional information is embedded in it. I would like to thank you for your attention, and here's my contact information. If you are interested on doing research in this area or want to discuss some questions, please don't hesitate to reach out to me. Thank you.